Hello, everybody, and good afternoon. I'm Alessandro Bertacchini, Sales and Business Development Manager in Turboden. Very happy to be here virtually with you today, and I hope you will enjoy this presentation about the decentralized waste to energy. Let me take you through the agenda first. I will start with a brief introduction about Turboden and talk a little about circular economy and waste to energy first. Then I will describe the organic ranking cycle technology and how it is used in decentralized waste to energy plants. At some point, I will give the floor to Simon Webb, Managing Director in Tidy Planet. With Simon's help, we will see some technical solutions for RDF and SRF and a couple of case studies. At the end, we will be both me and Simon available and happy to answer any question you may have. Okay, lots of irons on the fire, so let's start straight away with few information about Turboden first. Turboden was founded in the 80s by Mario Gaia, a professor at the University of Milan. Nowadays, Turboden is a global leader in the design, manufacture, and maintenance of organic Rankine cycle technology for heat and power generation. Size of our ORC ranges from 500 kilowatt electric up to 20 megawatt electric with a single shaft turbine. Since 2014, Mitsubishi Heavy Industry owns 51% of Turboden shares. As part of the power system domain, we in Turboden leverage the strength of MHI Group as well as the technical and financial support. We are present in more than 45 countries with about 400 plants in many different fields of applications. We are in renewables, such as biomass and geothermal, for instance, industrial heat recovery, combined cycles with gas turbines and engines, and waste to energy, which is the topic of today's presentation. Average availability among our fleet is 98% with almost 18 million working hours and 22,000 gigawatt hour of power generation in total. Most of our clients has an after-sales contract in place, which we take care firsthand. And that gives us a lot of experience on our system. Our presence in UK is also important, with 14 plants in operation and 2 more contracts in execution as we talk. Both those are due to start up by mid of this year. Most of our references in the UK are CHP systems between about 1 and 3 megawatt electric. The larger power plant is in Sheffield area, and it's a 6 megawatt electric power only ORC turbo generator from waste wood and RDF combustion. Okay, that was a quick company profile. Let's jump now into the main topic, circular economy. We hear a lot about it since in 2018, the European Union has adopted the circular economy package. According to the waste hierarchy, the priority is to adopt new technologies and policies that minimize waste creation first. However, there will always be some residual waste left, which is contaminated or too low quality to be recycled. For this reason, the challenge is to find out how to keep the material cycles clean, how to treat securely the waste left after recycling, and how to use the value in residual waste. Waste to energy answers those questions, helping to keep the circular economy clean. In fact, the main purpose of waste to energy has always been volume reduction and sanitization. Now, it is also more and more about waste valorization. In fact, with waste to energy, it's possible to recover more than 90% of the energy embedded in waste, and at the same time improve the recycling quality and rates, because metals and minerals can be both recovered from the bottom ashes. In addition, we must say that waste to energy contributes to fight climate change, of course, and global warming by diverting waste from landfill and by substituting fossil fuels in energy generation. The new circular economy principles introduced by the European Union will have implication on the design of new waste thermochemical treatment plants. Let's look at some of the criteria listed here. For instance, the preference for CHP systems and the proximity principles together suggest that waste should be available locally and plants built nearby heat users in order to achieve higher efficiency rates. Also, by prioritizing separate and selected collection of municipal solid waste, the residual waste availability will most likely decrease over time. That means new plants should be designed to treat smaller quantities of waste with a higher low heating value than in the past, as a consequence of the efficient sorting and mixing with special waste streams. So to sum up, we can say that along with traditional energy from waste plants, a modern infrastructure of smaller and efficient plants placed in strategic locations should be developed. The immediate advantage of that will be to reduce the costs of waste logistics, as well as the impact to the road traffic and the CO2 emissions. Also, with a small footprint and lower chimney stack, the impact on landscape is minimized, and it may be faster to get planning and authorizations. Communities could eventually become self-sufficient in their heat and power requirements and maybe have a higher perception of the direct benefits brought to them, which is not really the case for big plants. Finally, being able to valorize both heat and power together with high availability and low operational costs could guarantee faster returns to shareholders. Okay, I would like to talk now about the organic ranking cycle technology. That is what we do in Turboden. The picture shows how easily our ORC turbo generators integrates in waste-to-energy plants. In few words, the heat available from waste combustion is recovered and exploited to generate thermal power and electricity. But let me explain you more deeply how in detail. The heat available from the primary thermal treatment is collected and conveyed to the ORC system by an intermediate heat carrier, which in most cases is thermal oil. In the evaporator of the ORC, the working fluid is vaporized to expand into the turbine for power generation. Exiting the turbine, the vapor goes into the generator for internal heat recovery first, and then it is cooled down and condensed. Finally, the working fluid is pumped back into the cycle again. The whole system is a closed loop designed to be durably tight, avoid area classification, and ensuring negligible fluid replenishment. As you can see, condensation can happen at different temperatures, depending if priority is the electrical efficiency or heat cogeneration for heat purposes. Okay, so what is the difference with a steam turbine? Here are the main difference with a traditional steam ranking cycle. First of all, ORC uses an organic fluid instead of water. The main thermodynamic difference is that water steam must be superheated while organic fluid vapor doesn't. Organic vapor expands in the turbine without liquid formation. Reason why there is no risk of blades erosion. There are also some practical differences. In steam turbine, the water quality is an issue and water treatment plant is required and is critical in most time. Due to the pressure involved, steam turbine needs to be supervised continuously by patent personnel, while ORC is automatic and there is no need to attend operations. Another difference to mention is related to the low flexibility of steam turbine, as it is shown in the next slide here. This graph compares flexibility and electrical efficiency behavior at partial load for the two systems. As you can see, when ORC is fed with half of the load, for instance, the electrical efficiency is as high as 90% of the nominal one and stays at 80% when the input drops down to 30%, let's say. While steam technology, on the contrary, shows a stronger decrease in efficiency when not working at design conditions. Okay, last slide to conclude the comparison, to show how for a given input, a steam turbine will have far more stages with shorter blades than an ORC turbine. And this is due to the higher molecular mass of the working fluid. For the same reason, the turbine speed in ORC system is also quite low, only 3000 RPM. So altogether, low speed and larger diameter means robust design with lower mechanical stress, less maintenance requirements, and a longer life, of course. Okay, I'm done now with the technical slides, but before giving the floor to Simone, just few words about waste management in UK, or at least how I see things from here, from Italy. Everybody recognizes the UK has done a great job to reduce waste landfilling since 2000-2001. However, the amount of waste sent to landfill in England rose by 4% last year, which is the highest figure in the past 10 years. I understand that maybe due to the increased cost in waste exports, at least I read that there might be several reasons that altogether contributes. For instance, I read about the taxes being imposed by receiving countries such as the Netherlands and import bans applied worldwide. There is also kind of a Brexit effect playing here, I think, with some uncertainty on the new legislative framework and duties being introduced or on the site at least. And most recently also, of course, the logistical impacts caused by the pandemic of the coronavirus, which effects are yet to be clearly reckoned, I guess. So an increasing number, for all those reasons, an increasing number of organizations seems turning their attention to the value of waste, especially RDF and SRF, and decentralized waste-to-energy plants is perhaps a good, sustainable, and circular way to valorize the waste. We briefly saw already the advantages of having smaller plants, and I understand there are also some specific drivers that makes this concept even more appealing in the UK. Here are some of the reasons, drivers listed out. I'm sure you know them better than me, and I will be happy to discuss all that with you later, if you like. But now it's time to hear more from Soundweb on the solutions available to valorize waste at best. And perhaps he will speak also a little bit more about those drivers. Please, Simon, the floor is yours. Thanks everybody for the attention so far. Enjoy the rest of the presentation.
Hello, I'm Simon Webb, Managing Director of Tidy Planet, and I'm delighted to be part of the RWM virtual exhibition today. We are a distributor for Turboden and Sugimat's exclusive distributor in the UK, and have worked with them for the last 6 years, developing their presence in the UK market, following our first project that we completed together in 2016. This project was for Gatwick Airport, where we designed and installed a turnkey waste-to-energy solution for 15 tonnes a day of non-recyclable wastes that were recovered from the airport's recycling facility. The system we installed processes and dries the waste from the airport's terminals that contains a lot of contaminated food wastes. This waste is fed to the IED-compliant Sugimat boiler, where it produces energy for the recycling facility. The RDF we produce on this site is very dry and has a high CV and high ash content, but very low bulk density, and is in many ways a difficult fuel to use than many RDF materials. But with Sugimat support, this has been a great project to work on, and the system runs very well. After Alessandro's presentation, I don't need to tell you about Turboden, other than their ORCs are perfectly matched with Sugimat's boilers in order to produce energy from waste. Sugimat have been manufacturing solid waste fuel boilers in Valencia for over 40 years. During this time, they've installed over 3,000 systems in sizes ranging from 30 kilowatts to 50 megawatts. Whilst their speciality is thermal oil boilers, they also produce hot water and steam boilers. Our role in this partnership is to bring the projects together and deliver them for the customer. We've over 20 years experience in project delivery in many areas, and for the last 10 years we've been working in the energy from waste sector. Both Sugimat and Turboden have a number of references for solid waste EFW facilities where the systems are connected together, and a list of references is in the table to your left. In addition to our first RDF waste to energy project for Gatwick, we're currently working on 2 new RDF EFW facilities that will be in operation towards the end of this year. These projects will both use Sugimat's boilers and Turboden's ORCs. The first of these is a CHP project where all the heat and power will be distributed to a hospitality venue, heating and powering a number of properties on the estate, as well as the racecourse and racing circuit. The second project is a replacement boiler to power an existing Turboden CHP system on a site that is struggling to find enough reasonably priced biomass to make its wood chip boiler viable. They've identified that the business case for the use of locally sourced RDF is far more sustainable, and we will be replacing the wood chip boiler for one designed specifically to meet their new requirements. I'd now like to explain a little bit about thermal oil boilers for those of you who may not be familiar with them. Like steam, thermal oil boilers operate at a much higher temperature than hot water boilers can. And although hot water can be used to power an ORC, it's not very efficient. For the thermal oil circuits connected to an ORC, we typically operate at 310 degrees centigrade and a pressure of less than 6 bar, which is the head pressure from the pump. With boiler efficiencies of up to 86% and fewer circuit losses, thermal fluid compares favourably to steam in many applications, particularly in small-scale energy recovery facilities like those we're talking about today. Although most of the EFW systems in the UK are large-scale mass burn facilities, there's been a definite shift towards smaller-scale great combustion solutions over the last few years, and this has prompted Sugimat to develop their business in this direction. Last year, Sugimat released their newest boiler design, the Horizon Plus horizontal boiler. This was conceived by Sugimat's technical director to solve the performance issues created by high ash content fuels such as RDF. Another recent development of Sugimat's is the computer vision control system, which replaces the need for regular manual observation of the combustion process. Integrated into the boiler's controls is a high-performance image recognition system, similar to that in a Tesla car. This can recognize the difference between flame, embers and ashes, as well as the flame intensity, in order to automatically determine and control the combustion of the fuel. This is particularly important with waste-derived fuels, as they're quite variable and the combustion requires continuous monitoring and adjustment. Sugimat's system is able to manage all of the combustion parameters based on the conditions inside the combustion chamber and make corrections in real time instead of relying on a boiler operator to do so periodically. The benefits are lower emissions and improved combustion and efficiency. I'd now like to provide you with a little technical information on the two main types of thermal oil boilers that Sugimat manufacture. Firstly, the traditional vertical coil and battery design that they've been producing since 1993 and can be seen in the photos on the right of the screen. In these boilers, we have a number of different grate and furnace designs, all of which are bespoke to the customer's requirements. For most solid waste fuels like SRF and RDF, they use an inclined step grate, as this is the proven solution for these materials. The furnaces are equipped with primary and secondary air and NOx-reducing flue gas recirculation. Typically, a preheating burner and computer vision systems will also be installed in the furnace. After the furnace, an adiabatic chamber is installed to maintain the gas temperatures at above 850 degrees for at least 2 seconds, in order to keep the gases at the required residence time and temperature to ensure complete combustion and to comply with the Industrial Emissions Directive. This chamber is brick-lined and insulated to minimize heat loss, and the gases pass through here on the way to the first boiler, which is normally a single-pass radiant coil. As the gases flow in an upwards direction through the coil, any heavy particles of fly ash that haven't fallen out in the adiabatic chamber will fall out here, and this minimizes the amount of ash reaching the second set of boilers. The radiant coil is able to operate at higher temperatures than the batteries, and the gases that entered at above 850 centigrade will leave this first boiler at less than 700 centigrade, as this is the upper limit of the heater batteries. The batteries consist of a matrix of smaller tubes that are more efficient than the coil boiler and are typically oversized to recover more heat as the coil becomes less efficient over time due to ash fouling. The coil boiler is normally cleaned manually once or twice a year, whereas the batteries are automatically cleaned with high-pressure compressed air every few hours in order to maintain their efficiency and performance. All of the ash that's removed from the furnace, adiabatic chamber and the boilers is directed to the automatic ash cleaning systems and onto the ash disposal points, one of which can be seen in the center of the top picture. The vertical boilers are suited to fuels with up to 20% ash content and can heat thermal oil up to 400 degrees centigrade with an efficiency of 86%. Sugimat's recently developed Horizon Plus boiler was conceived by their technical director in 2017, and after several years of development and testing, it was granted a patent in 2019. As you can see from the images, the boiler rotates on casters, which encourages any ash deposits that naturally fall off to follow the spiral of the tubes and make their way out of the boiler in the same direction as the gas flow. If the ash doesn't naturally fall off the tubes, cleaning media such as sand or aggregates can be introduced into the gas flow from the furnace, and these recyclable materials help to dislodge the ash from the coils and keep the boiler surfaces clean, which guarantees consistent performance of the boiler. As this system is able to overcome the problem of ash sticking to the coils, it's possible to have a 3-pass coil where the gases flow past several sets of tubes rather than a single set, as in the single-pass design of the vertical boiler. This means that the design of the boiler is capable to recovering energy from the gases without the need for heater batteries. This brings a number of advantages, including stabilizing performance and efficiency, whilst eliminating the need for high-pressure compressed air cleaning systems. The horizontal design reduces the height of the system, and it can be much lower than with the vertical design, and this means lower buildings, less cost, and potentially an easier route to planning approval. The Horizon Plus can operate at up to 310 degrees centigrade as required by the ORC, and notably it can still operate efficiently with a higher ash content fuels of up to 40%. I'd now like to move on to an example of small-scale decentralized energy recovery facility that we're standardizing for RDF and SRF applications. With a maximum fuel input of 3 tons of non-hazardous waste per hour, the system falls under the Small Waste Incineration Plant Permitting Scheme in England and Wales. Unlike larger scale systems, the SWIP scheme is permitted by local authorities rather than by the Environment Agency. And although the requirements of both schemes are the same, currently many local authorities are able to process the applications quite quickly and in less than 6 months. Whereas anyone who's applied for a permit from the Environment Agency recently will tell you it's a far lengthier process. As the calorific value and RDF of SRF and RDF are very different, with the same amount of fuel limited at 3 tons per hour, you can produce up to 12 megawatts with a high quality SRF, compared to around 6 to 9 megawatts with lower grade RDF. At this size, Sugimat can produce both vertical and horizontal versions of the boilers, and both come with guaranteed availability of 8,000 hours per annum and efficiencies of up to 86%. The typical layout requires less than 2,500 square meters, which makes it easier to locate closer to areas that generate waste, which lends itself to decentralized solution. As the electrical power output from the ORC is less than 3 megawatts, it's often easier to find a cost-effective grid connection at this size, which means it can be sited more easily than would be the case for larger systems. This makes it possible to go from inquiry to operation in less than 18 months. Here you can see a mass energy flow of a typical RDF or SRF facility. With a good quality RDF with a calorific value of 14 megajoules per kilogram and limited to 3 tons of fuel an hour, you can produce around 9 megawatts of heat, which will generate 2.3 megawatts of electricity. If you compare this to SRF, which is a higher quality fuel, you can generate around 3.2 megawatts of electricity with the same quantity of fuel. Both of these systems use Turboden's high efficiency electricity only air-cooled condenser ORCs, where the rejected heat is dispersed to the atmosphere after condensing the ORC fluid. An alternative CHP version of the ORC would be able to produce up to 10 megawatts of hot water, as well as a slightly lower amount of electricity, and this is a preferable solution wherever the hot water can be put to good use. Looking at a typical business case for a 3 ton an hour SWIP system using 25,000 tons per year of fuel, you can see it's possible to have a very strong return on investment. The gate fee for RDF varies around the country, and for this example I've used a good quality RDF with a calorific value of 14 megajoules per kilogram, which would attract a gate fee of around £90 per tonne, generating an annual gate fee revenue of over £2 million. After the ORC and boiler's parasitic load has been deducted, you have 2 megawatts of electricity that can be used on site or exported to the grid, or even used to generate around 800 kilograms of road transport hydrogen, which is topical at the moment. We then deduct the annual reactive and preventative maintenance costs, which include the spares used over 10 years and the abatement consumables needed to comply with the emission regulations. Next, you have to consider the ash disposal costs, unless you wish to manufacture your own concrete products, which is permissible from this type of ash. Finally, although it's possible to leave the system unmanned for 12 hours, we've allowed for personnel to supervise the system around the night. With a budget of around £10.5 million for a turnkey EPC solution, excluding grid connection, site and civil costs, the return on investment is less than 3 years for sites that can use the electricity to reduce their own grid consumption, and less than 5 years for a site that exports their power to the grid. When compared to RDF, many of the return on investment elements are similar to SRF, and the main difference with a higher quality fuel with a higher calorific value and a lower gate fee is that the benefits from these two income streams are reversed. As the waste has been further processed to produce the higher quality SRF, it costs more money to produce and so attracts a lower gate fee. However, as it is higher quality with a higher CV, you produce more electricity from every tonne you consume. Although the gate fee reduces by around £500,000 per year, as you produce more than 50% more electricity, the annual return on investment is slightly better than with RDF, if you can use the energy on site. However, if you can only export the electricity, you would be financially better off with the return on investment with a facility consuming RDF. As both the boiler and the ORC are larger with an SRF facility, the capital costs are slightly higher at £11 million, but the return on investment are very similar at 3 to 5 years. Finally, should you wish to produce more energy than can be generated by a SWIP-size system, then Sugimat can produce a single boiler with up to 30 megawatts thermal capacity, or two 25 megawatt boilers can be connected to a single ORC to produce up to 12.5 megawatts of electricity, as can be seen in the photograph on the right. All of the boilers are IED compliant and can meet the more stringent emission requirements for the WI BREF, the new standard for best available technologies in waste incineration. And although incineration is a dirty word in our business, the emissions from the system you can see on the right are not. Many thanks for your interest and time today, and we look forward to hearing from you with any questions. Thank you.